Okay, so bonjour, hi everyone. Welcome to today's seminar, where we have an excellent speaker, Alfredo Torrico. Alfredo, he has a PhD in operation research from Georgia Tech, and he's currently a postdoctoral fellow at the Canada Excellence Research Chair in Data Science for Real-Time Decision Making at Polytechnique, Montréal. And today he's going to talk about one of his research interests that are matching markets. So thank you very much, Alfredo, and the floor is yours.
Thank you, Margarita, for that introduction, and thank you everyone for being here today. So the topic of today is matching markets, and I'm going to explain you a little bit two projects that are related to subset selection in these kind of markets. Okay, so matching markets can find application in several aspects of our lives, and the basic notion of a matching market corresponds to an assignment problem in which you pair entities from two different sites. And also it's important that in this kind of market, the money doesn't play necessarily the main role to clear the market, but instead the preferences of the participants are more important. In particular, both sides must agree in order to generate a match. Okay, so one example of this is the school admission market, in which you want to allocate students into schools according to their preferences. Other kind of market in which money doesn't play a role at all is a gig exchange. And here you want to design mechanism in which you want to exchange this indivisible item according to some rules. Okay. In dynamic settings also you can find matching markets, for example, in online advertising, where one side of the graph is fixed and the other side arrives sequentially over time, and you want to when an entity arrives, then you want to match it or discard it. Okay, so surprisingly also these find applications in refugee settlement, because people are arriving over time, and then you want to allocate these people to certain cities in order to maximize their success. Okay, so with the progress of technology, also online matching platforms have grown in popularity, and also they provide services in many areas such as ride-hailing, ride-sharing, labor, dating, and also accommodation. Okay, so the main characteristic of matching markets in the design is that agents have preferences, and ideally both sides must agree in order to generate a match or a transaction. But the matchmaking process can differ depending on the application. It could be centralized, for example, and where there is only a central decision maker that takes the decision. For example, in a school admission, there is one clearinghouse that takes the final allocation. Or it could be decentralized in the sense that some matching platforms only provide some recommendation, but at the end, the decision of a match happens between the participants. Okay, this process also can be static, meaning there is only one shot decision. For example, in school admission, there is only one allocation. Or it could be online, for example, in ride sharing, in which requests arrive sequentially over time, and you have to make decisions dynamically. In terms of communication, there is also differences depending on the application. It could be one directional, meaning that one side initiates the process. For example, in accommodation, usually customers first decide, and then the host is going to reply according to those decisions. Or it could be two directional in the case, for example, in a dating platform in which any of the two sides can initiate a match. Okay. So recently has been some concerns related to the presence of bias in many of these platforms or other societal issues around the matching markets. So you may consider some societal consideration into your model, such as maximizing social welfare or including some fairness or diversity constraints. Okay, so matching markets have been studied from different fields, such as computer science, optimization, or game theory and machine learning. Okay, but I want to highlight a few of these works. For example, the basic idea of an assignment problem comes from the 1700s, and the idea there was to match cities in order to transport some good. Okay, later Hitchcock and Koopmans in 41, they provide this linear programming formulation for this model, and and also give some geometric interpretation of the optimal solution. So if you add some more complexity, for example, the preferences, We can go to the Gale-Shapley in the model of the Gale-Shapley in 1962 called the stable matching problem. There is a long line of research related to this problem in terms of how the structure of the preferences or also different constraints of the problem. In the case of the kidney exchange, this idea of exchange as an indivisible item was introduced by Shapley and Scarf in '74 in a housing market. But then Roth, Sommes, and Umber provide the first model for kidney exchange that has grown in popularity in different countries. And there has been a lot of a line of research related to how different mechanisms of exchanging and also the complexity around this problem. Finally, I want to highlight this online bipartite matching. The idea, this dynamic matching was proposed by Karl Pasirani and Basirani in the 90s. And later on, it found applications in online advertising. For example, Meta and others proposed, and in 2007, the first model for online advertising, in which one side is fixed and the other side arrives sequentially over time. There is also a long research literature related to this problem, especially in terms of how you can model the arrival of the entities, or kind of benchmark, what kind of benchmark you consider to compare your algorithm. Okay, so I promised subset selection in this talk. So subset selection corresponds to a combinatorial problem in which, under limited resources, the decision maker cannot choose all the available options. So they must choose a subset of them. Okay, so I want to exemplify this. So for example, in the front display of a bookstore, you can only choose a subset of the books. In this case, the limited resources space. Or if you want to open new Putinville restaurants, the resource here, the limited resource is money. Or for example, designing the lineup for the Oceaga Festival, the resource is time and money. Okay. In the case of matching markets, the limited resource is supply. For example, an Airbnb host cannot admit 2 customers at once, or schools have limited number of spots. Okay. So in the first case, preferences may lead to frictions in the market because there may be some accommodation that are more popular than others. So many customers may choose the popular option. And in the second case, a limited number of spots in school can lead to undesirable allocation for the students. Okay, so in this one, we're going to see that showing a subset of options for the first case may improve the efficiency of this kind of market. And for the second case, we're going to see that expanding the capacity of a subset of schools, it improves actually the final allocation of the students. Okay, so my main message here is that by incorporating a subset selection component as part of the model, may serve as an attractive tool to expand the decision space of decision makers and consequently improve the quality of the final outcome of this matching market. Okay, so in this setting, my research contribution has been mainly in 2 areas. One is matching markets and the other is subset selection in the area known as molar optimization. But I also worked in risk-covered routing and recently on diversity topics. But for today, we're going to focus on matching markets. And the first message that I want to say is that assortment planning can be used as a tool to improve the efficiency of the market. And for the second part, I'm going to show you that capacity expansion can be used also as a tool to improve the allocation of the students. So we're going to see these 2 parts in this talk. Okay. Let's go for the first part. So this is joint work with Margarita Carvalho at University of Montreal and Andrea Loy now in Cornell Tech. And this work is related to assortment optimization in this sequential matching market. Okay, so the main question for us is how the display of options can improve efficiency in this decentralized matching market. Okay, let me give you an example to clarify that. So let's say that we have 3 customers, okay, and they're looking for accommodation, let's say in Montreal. And we have 6 options that the platform can show to them. But in the middle, we have a popular option that is given by some ranking, okay, that is highlighted by this star. So let's say that the platform chooses the following subset of options to show to these customers, okay? The problem is that everyone is seeing this popular option, so this may lead to the first issue, which is choice frictions, okay? Why? Because the host can only choose one bag, okay? So this results in a suboptimal solution. Okay, so the platform then may prefer to show less options to the customers in order to avoid these frictions. but that also could give us another issue, that is that some participants may leave the market. So we have to balance these frictions and recommendations for the customer. Okay, so if we show these following options, then we can improve the number of allocations. But given that we are given less options for some of the participants, then participants may leave the market. Okay. So the specific goal for this problem is we want to avoid inefficiencies in the market by constructing a specific menu of options so that the revenue of the final matching is maximized. Okay. So inefficiencies happen because of the preferences. So in our model, we incorporate preferences of both sides via choice models. I'm going to explain a little bit later on what is this. We're going to construct menus for only one side of the market, and the previous example was for the consumers. And finally, we have this corresponds to the assortment optimization part. And finally, we have the matching, which has some characteristics. It's going to be decentralized, meaning that the platform, once it shows the menus, it doesn't intervene on the matching process. It's going to be a static. There's only going to be one shot decision. Once I initiate the matching process, in the previous example was the consumers, and at the end, both sides must agree in order to generate a match. And this is the sequential matching part. Okay. I'm going to formalize this in the next slides. Okay, so there are several lines of research related to this problem. First is market efficiency, but this line of research has mainly focused on the design of platforms, mainly how we can limit information for one side and how this improves the number of matches, or how you can limit the number of matching requests. But this line of research has not focused on algorithmic methods. In our work, we focus on providing menus of options in order to avoid this inefficiency. The second line of research is assortment optimization in the static case. This problem corresponds to the following. There is a seller that wants to select a subset of items to show to a customer, a single customer, and the single customer is assumed to have some probabilistic choice among these options that he or she sees. Okay. The problem is that it only considers one customer and it doesn't consider the preferences of the other side. Okay. So there's a long line of research related to this problem in terms of how modeling the behavior of the customer and also some constraints on the menus of options. Okay. Finally, there is some new line of research related to assortment planning in two-sided markets. I will explain you the sequential matching market that was proposed by Ashlagi and others in 2020, but also recently Rio, Savan, and Jeng in 2021 have studied a model for dating platforms, and recently also Awad and Savan have studied some online version of this problem. Okay, so let's recap what is single customer assortment optimization. Let's say that a seller has a universe of items from which he wants to select a subset of options to show to this customer. In this case is Mr. White. Okay? So Mr. White comes to the store and the seller selects a subset S to show to this customer. And then the customer is going to assume to be probabilistic, meaning that there is a probability distribution over this subset plus the option of not buying anything. Okay, so formally there is a probability distribution P that is defined over this subset plus the upside option that is denoted here in this case by 0. Okay, so Mr. White is going to pick an element J from the subset with probability Pj of S. If that happens, then the seller gets revenue Rj. Okay, so the goal of the seller is to maximize the expected revenue of this problem. Okay, so wants to select a subset of options that such as maximizes the sum of Rj times the probability of selecting J from S. Okay, so the revenue of not buying anything, of course, is 0. Okay, so finally, I want to highlight that this part of the distribution, this sum, corresponds to the demand of the customer. Okay. Is there any questions on this topic in particular? Okay, so the question now is how we can include this kind of models for a two-sided market. So Ashlagi and others propose the following sequential matching markets. On one side, you have consumers, and on the other side, you have suppliers. And the goal of the platform is to select a menu of options, a menu of suppliers to show to each consumer at the same time. Okay, so in this case, we're going to select subset SI to show to the consumer I. And once that happens, once the platform shows the options, then the platform doesn't intervene on the following probabilistic process. Okay? So consumers see the options, and they are going to pick one of their options with some choice model, or they may decide to leave the market. Okay? Let's say that I selected J with probability now Pij that depends on the assortment that of the menu that is she's seeing. Okay. After that, each supplier is going to see the subset of consumers that selected them. Okay. In this case, J sees these two consumers, and among them, each suppliers are going to select one back, or they're going to decide to leave the market. Okay. In this case, J selected back I with probability Qji of Cj. That depends on this assortment that he's looking at. Okay. So a matching is going to happen. A match is going to happen if a consumer I and a supplier J sequentially select each other. In that case, the platform gets a revenue Rj. So formally, we have N consumers and we have M suppliers with different choice models, Pi and Qj. So the problem of internet for us is to select a family of menus that we're going to show to the consumers in order to maximize the expected revenue of the final match. Okay. And this expectation is with respect to the probabilistic choices that the participants have. Okay. Any questions on this model? Okay. So Achlagi and others, they proved that this problem is actually NP-hard, meaning that there is no efficient method to compute the exact optimal solution for the problem here highlighted in yellow. Okay. Let me give you some idea of the results so we can compare with our work. So Achlagi and others specifically consider two models. One is a multinomial logic for consumers that corresponds to the following. So let's say that consumers have published scores over the suppliers, okay, that is denoted by Vj, and the probability of choosing an element from a supplier from the menu is going to be proportional to the weight of the assortment, okay, plus the outside option whose weight now is 1, is normalized to 1, okay. So I want you to think that the value that they put on a stain in of choosing J is Vj, and the value of leaving the market is 1, okay. For the suppliers, it's also kind of a multinomial logic, but it's a uniform model in which now the scores that suppliers have over consumers is all the same, except for the outside score that is denoted at Uj0. Okay. So Achlagi and others focus only on maximizing the expected size of the matching, and only in the unconstrained case, meaning that there is no constraints on the menu of options, which might be not ideal for certain applications. As I said, they consider the same multinomial logic. Observe that the scores do not depend on the consumers. Okay. And also the suppliers follow this uniform model. They prove that in this case, this problem is NP-hard to solve. Okay. So the focus that they give is providing some algorithms with some provable guarantees in the following sense. So they want to give an algorithm that guarantees some alpha factor of the true optimal value. Okay. So where alpha is between 0 and 1. Okay. So they divide the analysis in two different settings. In the first setting, they want to consider when consumers have values at least 1, meaning that they value more the supplier more than to leave the platform. For that case, the factor that they obtain is 0.5%. Okay. For the other case, when the consumers value less to stay than to leave, then the factor that they obtain is 10 to the minus 3%. And as you can see, these factors are very weak in practice. They are not very meaningful, but at least we can see that they are constant. Okay, do not depend on the size of the instance, for example. Okay, both results are also independent of the magnitude of the outside score of the suppliers. Okay, it doesn't depend on Uj0. Okay. So in our work, we advance the state of the art in 3 main directions. The first direction is that we consider consumers and suppliers with more general choice models, or not only the multinomial logic. And also we consider heterogeneous preferences, meaning that we don't need to assume that consumers have the same model. Okay. For the second part, I mean, also we consider the revenue maximization case, okay, not only the size of the matching, and also we consider cardinality constraints. Okay, so the menus now has to be limited to a certain budget, okay, which is more suitable for certain applications. And finally, in this more general case, we show that we have significantly better approximation guarantees factors. Okay, our approach is based on several techniques. One is the model optimization, and also in based on linear programming formulation and corresponding rounding method for this problem. We also provide a tractable heuristic that we show that empirically outperform the rest of the benchmark and also can handle more general cases. And finally, in our computational study, we observe key factors that determine the structure of the ideal assortment depending on the regime that you're studying. Okay. Okay, so for the purpose of this talk, I'm going to focus on a specific kind of model to make it more easy to understand. So the problem actually becomes significantly harder to analyze when you consider more heterogeneous agents, meaning that now you have agents that have different choice models. The challenge in this case is that we need to balance assortments by accounting for the preferences of both sides. And as I mentioned, we are going to focus on different multinomial logic models. Okay. So for consumers, we're going to consider the following multinomial logic. Now it's similar to the previous work, but now the scores may depend on the consumer. Okay, so the scores is indexed by I and J. Okay. On the other hand, we have suppliers that also follow a multinomial logic model that is more general than the uniform. And I'm going to keep the notation for the outside scores just to keep some coherence with the previous work. Okay. So we analyze the following 2 regimes. We have the hard regimes in which consumers value less to stay than to leave, and when suppliers value more to stay than to leave. Okay, that's a hard regime because we have to balance. We have to show enough options to consumers so they leave, but also not enough options so they don't produce congestion in the market. Then we have the easy regime in which consumers value more to stay than to leave. In this case, we have to show some enough options so they leave. So they stay. And actually, we have to show only one single idea supplier in this case. Okay, so the structure of the assortments depend actually on the regime that we are studying in our problem. Any questions so far? Okay, so let me give you an idea of our results. We divide then in the hard regime, in which all consumers satisfy this condition, and also suppliers value more to stay than to leave. So we give an algorithm that returns a solution that guarantees 15% of the true output. Okay, and this is valid with or without constraints, but the method that we use are different. For the easy regime, when all consumers satisfy this condition, then we have an algorithm that guarantees 31% of the true output. Okay, and this is also valid for constraints or without constraints, because actually our menus consist of only one supplier. Okay. Now, if we want to compare with the previous work, the first result is valid for Ashlagi and others when the values are less than 1, and also when the outside score satisfies this condition. And we see that we significantly improve from 10 to the minus 3% to 15%. For the easy regime, it's also valid for the model studied by Ashlagi and others, and we see that we drastically improve from 0.5% to 31%. Okay. Finally, also, if you want to consider no constraints on the regimes for the consumers, meaning that you don't divide between these less than 1 and more than 1, then we can provide a guarantee. Actually, we provide a factor of 7.9%, but we have to restrict our scores to be all the same, meaning we have the same model for consumers. and as long as the supplier satisfies this condition of preferring more to stay than to leave. Okay. Okay, so the key idea for the first result is that we construct a fractional assortments via a linear programming formulation of this relaxation of this problem, and then we have to round appropriately. Given that we obtain a fractional solution, we need to obtain at the end output a feasible solution for the problem. The key idea for the second result is that we have to find these ideal suppliers so they are more likely to stay in the market. Okay, and we find that by using techniques from some modular optimization. Any questions on our result? Okay, so let me give you a brief idea of what the main algorithm for the hard regime is. We're going to consider only the cardinality constraints, and then I'm going to mention briefly how to do the unconstrained setting. Okay, so let's say that menus have to satisfy this budget constraint for each consumer. So our problem has the following relaxation. We have the following upper bound for our problem. And in the objective, we are looking to balance the expected number of consumers that chooses each supplier. Okay, so that expected number of consumers corresponds to this sum inside of this minimum. So we're taking the minimum between 1 and the expected number of consumers that chooses supplier J. Okay, so by this minimum, we balance the number of consumers that each supplier gets. Okay? So I want you to think that Bij times Yij is our variable, corresponds to the probability that I select J. Okay, so the first constraint corresponds to that W and Y define a probability distribution over the menus. Okay, the second constraint corresponds to the fractional way of looking at the cardinality constraint, because you can see that Xij, defined as a ratio between Yij and Wi, corresponds to the probability of J being in the assortment. Okay, so this constraint in blue is actually the fractional cardinality constraint. And finally, we have that Y has to be less than W. That corresponds that X has to be less than 1. Okay. So the algorithm is the following. We solve this linear programming formulation, and then we set this X, fractional X, as the ratio between the Y, the optimal Y, and the optimal W. But now we have fractional solution. We need to output a feasible set of suppliers. We cannot have half of a supplier in an assortment. So for that, we use a technique that is known as dependent random mass rounding, and we use that independently for each consumer. Okay. Once that we round, we obtain this now integral solution, this X hat, and we define the assortments according to this indicator of the X hat. Okay. So this rounded technique was proposed by Gandhi and others in 2006, and it has 3 main properties. But the main one here for us is that it gives you an assortment feasible with probability 1. Okay. So now you may wonder, what do we do in the unconstrained setting? For the unconstrained setting, we don't need to output a feasible assortment because we don't have constraints. So instead of doing the dependent rounding, we can do the independent rounding. That is basically tossing a coin for each of the pairs I and J, okay, according to the probability Xij. Any questions on the algorithm? Okay, so let me move now to the experimental part of our work. Let's say that now we want to test our approaches for the easy regime. Okay, so they value more to stay than to leave, and we're going to consider the unconstrained setting. So we have 100 suppliers. We vary the number of consumers from 50 to 200. And the objective is to maximize the size of the final matching. So for each n, we run 20 random instances, and here in the plot, we are looking at the average of those instances in terms of the objective value. Okay. So first in green, we have an upper bound that we derive from some modular optimization. We also derive an upper bound from a concave relaxation that actually performs a little bit better. On the other hand, since it's unconstrained, we can show the full assortment, meaning that we show everything to each consumer. Okay, as you can see, it has this performance in dark green. And we also run this random assortment in which we include with probability a half any supplier to the assortment of each consumer. Okay. So as we can see, these two kind of assortments are dense in the sense that they are very large. And we see that the objective of our problem doesn't vary much under dense assortments. Okay. Since this is the easy regime, we have to only show this ideal supplier for each consumer. So is this the menu of option here is only of size 1. So we run our heuristic in red, and you can see that it's much better performance than the other two approaches. And in orange, we have this algorithm that finds the ideal suppliers. And you can see the sparser assortments, like smaller assortments, perform much better than dense assortments because they avoid this friction that you may have in this market, because the consumers prefer more to stay than to leave. So if we actually test another type of sparse assortment, just a random assortment of the same size that our algorithm, then we can see that the performance is very good. So not any sparse assortment is good for this kind of instances. Okay, so if now we move to the hard regime, where the consumers value more to leave than to stay, we are going to test the unconstrained setting. So for now, we have to show enough suppliers so the consumers stay in the platform, but also we have to avoid these frictions. Again, we have this smaller upper bound, and the concave upper bound actually performs similarly. For this setting, we can also show the full assortment and also the random assortment. As you can see, both perform similarly. But our heuristic also performs similar, which may indicate that, again, under dense assortment, since we have to show enough to each consumer, then the objective doesn't vary much with respect to these large assortments. Okay. So now if we test our algorithm that is based on this linear programming relaxation that I showed you before, the performance is similar up to 100, but then changes the behavior. There is this phase transition after 100 that is it might be because the objective that we're using in our formulation corresponds to the minimum between 1 and this sum, as you remember. And this may have multiple optimal solutions, but the algorithm is only outputs a sparse solution. Okay. And I want to clarify that with the following. So we are going to run a random assortment that mimics the size of the solution that we obtain from our algorithm. Okay. So in purple, we have this random 2 that, as you can see, it has the same performance up to 100, but then it drops drastically the performance, which indicating that our algorithm actually has a sparse assortment, but it's a good sparse assortment. Okay, so the second observation is that we may have multiple optimal solutions, but the algorithm is choosing the good sparse assortment. Okay, so now I want to exemplify the cardinality constraint setting and how it affects these budget constraints on the quality of the outcome. So let's say that we limit the number of suppliers to be at most 5. Okay, this is a hard regime, meaning that consumers value more to leave than to stay. So again, we have this concave upper bound and our heuristic and our algorithm. So as you can see, again, we have this phase transition after around 125. That is also because of the objective that we're using in our linear programming formulation. But now the random assortment, since it's limited to 5, then it has a poor performance. So a trivial benchmark do not perform necessarily good under cardinality constraint. But if we increase the cardinality to 25, now dense assortments actually may perform much better. Okay, so random assortment actually improves this the performance from 5 to 25, from cardinality 5 to 25. Okay. Any questions on the experimental side? Okay. So actually in our work, we provide guarantees for a wider class of choice models. Under my assumptions, we can handle suppliers with a larger class of choice model known as random utility-based models. Multinomial logic is just one case of that. And actually, we obtain the same magnitude in terms of guarantees for this more general setting. Okay. But there are several open questions in our work. The main one that I want to highlight today is that handling heterogeneous preferences is much harder, meaning that you have consumers with different choice models, but you don't want to divide the regimes between hard and easy. So you want to combine these consumers that they prefer more to stay than to live, and others that prefer more to live than to stay. Okay. So one possible option for that is our heuristic, but in our work we don't provide, we were unable to provide a guarantee for this heuristic. Okay. So as we saw in this work, we contribute through three main directions. We generalize the choice model that was previously studied. We also consider more general objective and cardinality constraints, which is more suitable for applications in real life. And in this more general setting, we actually also provide better approximation guarantees. We give this also tractable heuristic for the multinomial case that we show that empirically outperforms the rest of the approaches. And in the experimental section, we saw two things, that in hard regimes, meaning that the consumers want to live more than to stay, then dense assortments may be preferred because you have to induce them to stay in the market. And dense assortments perform well in this synthetic data. Okay? In the easy regime, some sparse assortments, some smaller menus perform actually better than denser menus, than larger menus. Okay. So the main message is that assortment planning can be used in this kind of market as a tool to improve the efficiency of the matching market. Okay. But also our work provides some new insights to complement the design of matching platforms. But you also can consider different variants of this problem. For example, which side initiates the process? We consider only the side of the consumers, but if the market is unbalanced, then you may consider all kind of options. We also saw a sequential type of matching. So one open question in this case is that what happens if we have simultaneous matches in a dynamic setting? Imagine in a dynamic setting, you have to decide in every step the assortments. So as matches can happen sequentially over time, or matches can happen in the same stage. Okay. Also, in our work, we consider single choices from the participants, but the question is now what can happen for multiple choices. Okay. So in a recent work with Ignacio Rios and Victor Verdugo, we studied a dynamic two-sided matching model that is inspired on online dating apps. Okay. This model is dynamic, is decentralized as well. And we want to show assortments to both sides of the market. Okay, any side of the market can now initiate the matching process. In a preliminary work, we focus on a two-stage model, and we also provide guarantees for this case. And our technique looks to balance between this, as I mentioned, this sequential and simultaneous matches. And actually, we observe that sequential matches are preferred for the efficiency of the platform. And assortment planning can be used as a tool to induce these sequential matches instead of having matches in the same stage. Questions so far on this section of the talk? Okay, so now I want to move to a different application domain. I want to move to the college admission problem. This is joint work with Federico Bobbio, a third-year PhD student in University of Montreal, and also Margarita and Andrea. And the high-level question that we have in this is that how does the assignment of extra spots can actually improve the allocation of the students in this market? Okay. So the main question in this kind of market is how students should be matched to colleges. So Gale and Chaplin in 1962, they proposed this two-sided market, in which the participants reveal the preferences in terms of rankings. And there is a central decision maker, there's a clearinghouse that at the end decides the final allocation of the students in the schools. Okay, this has been applied in different settings and different admission process, such in schools in Boston and New York City, and also college admission in China and Germany, but as well in hospital and resident allocation in Canada, also in the US. Okay. However, recently has been some concern in terms of the quality of this allocation, particularly in how we can expand the access to certain minorities and also improve the diversity of this allocation. So from the technical models, the community has proposed different settings. For example, by defining what is a fair matching, or defining equal opportunity, or imposing quota constraints. Okay, but in our work, what we look is how the expansion of the market can actually improve the allocation of the students. Okay. So Gale and Chaplin in the 1962 proposed the following model. We have students on one side, and we have colleges on the other side. And a matching is going to be a subset of the edges between these two sides, such that each student is matched to at most one university, and each college is matched to at most Q sub U students. Okay. But now students and colleges have preference over each other. Each student rank the colleges, and each college rank the students. The preference, we're going to assume that are strict, meaning that there are no ties. And also they are going to be complete, meaning that each student rank all the colleges, and each college is going to rank all the students. We say that student S prefers college U to U prime if the rank of U is less than the rank of U prime. And we say that college U prefers S to S prime if the rank of S prime is less than the rank of S. The rank of S is less than the rank of S prime. So Gale and Chaplin in the 1962, they provide an algorithm that finds a matching M without blocking pairs. That means that there is no pairs student college such that both prefer each other instead of the allocation that they have in the matching M. Okay. So technically that means two things. It means that S prefers U to the current match in M of S. And second, that the capacity of the university is not full, or that U prefers the student S over some student in the matching M of U. Okay. Any questions on this part? Okay, so a matching without blocking pairs is known as the stable match. Okay. So let me give you an example of that. Let's say we have 3 students and we have 3 colleges. Each college is with capacity 1. Okay. So, and the rankings are denoted in this black box. So for example, A ranks first B, and then U, and then W, and U ranks first A, and then C, and then B. Okay. So believe me for now that the edges in gray corresponds to a stable matching. Okay. And actually is the best matching, the best stable matching for the students. Okay. So let me formalize that. Given a matching M, we're going to denote the average college rank as the sum of the ranks of the rank of the university that the students were allocated. Okay. So the average of the college rank in this example is 4. I'm not divided by the number of students, because A is ranked to the first choice, B is ranked to the first option, and C is ranked to the second option, which finally is 4. Okay. So Gale and Chaplin, actually the algorithm can be tailored to give you the best stable matching for students, and that corresponds to the stable matching that minimizes the average college rank. Okay. So the question now is, what if we increase the capacity of B, for example, from 1 to 2? Okay. In this case, now the matching in gray is not stable anymore. Why? Because C prefers B over U, and the capacity of B is not full. Okay. So we could move C to B and obtain a matching now with objective with the average college rank of 3. Okay. And actually, this is a matching that is the best for the students, because everyone is allocated in their first choice. So this idea of expanding the markets has been studied before from a game theoretics perspective, and is known as the entry comparative static. For example, Cominers in 2014 shows that by adding a new college, then all the students are better off, or by adding a new student, every college is better off. Okay. But instead, in our work, we take an optimization approach. Okay. Now let me formalize that. So the question for us is, which subset of K colleges should they have their quota increase to get the best student optimal stable match? Okay. So let me introduce some notation to formalize our problem. We're going to have a vector T indexed by colleges, And we denote by gamma t the instance of the problem which the capacity now of the college is QU plus TU. Okay. So given a budget K, we want to solve the following problem. So we have two decision variables. We have T is the allocation of extra positions, and the stable matching M of sub T, which is a stable matching in this new instance gamma T. Okay. So you can see now that we are minimizing the rank, the average college rank, and the allocation has to satisfy this budget constraint. We can only allocate K extra spots. Okay. So in our work, we show that actually this problem is NP hard, meaning that there is no efficient algorithm to obtain the true optimal solution of this problem. Okay. So instead, we look for an exact method that can handle some real-life instances. So our problem can be formulated as an integer programming formulation with quadratic constraints. We have a function that also gives you an exact solution, and we test this linear reformulation with in some synthetic data, and we also tested two different benchmarks. So in our computational study, we show that our exact method can solve instances of the size of 2,000 students and 15 colleges in under an hour. And we also studied two benchmarks. One is based on a linear programming formulation and also greedy, and we show that these two have a gap less than 20% when you compare to the exact method. Okay. Just to give you an idea of the quality of our solutions, is that, for example, if we have 1,000 students and 15 colleges, and you want to add 30 new spots, then now 15% of the students, meaning 150, are now admitted to the most preferred college. So by adding 30 new spots, you can significantly impact the quality of the allocation of the final match. Okay, so in an ongoing work, we are trying to study polyhedral structure of the feasible region in order to design an exact method that can handle large-scale realistic instances. Because, for example, in the school admission process of New York City, there are 80,000 students and 800 students. So you may want to design a heuristic that can handle those kind of large instances. So the main message for this section was that the increase of the capacity can serve as an algorithmic tool to improve the allocation of the students in this matching market. Any questions on this part? Okay, let me move to the final part of the talk. So we saw new models for two-sided matching markets with a subset selection component. The main message in the first part was that assortment planning can be used as a tool to improve the efficiency of decentralized matching markets. We saw that assortment planning is actually in two-sided markets is much harder than the vanilla version, meaning the version in which you have only one consumer. In the second part of the talk, we saw that by adding new spots, then we can improve the allocation of the students. And actually, even though this problem is hard theoretically, tractable exact method can deal with medium-sized instances. Okay, so as I wanted to say that powerful tools from multiple fields are required to address these new technical challenges that appear in these matching markets. And subset selection can serve as a tool, as I say, as an attractive tool that can expand the decision space of the decision maker and consequently improve the quality of the outcome. And with that, I would like to end my talk. I'm happy to answer any questions that you may have. Thank you very much.